Okay, good morning. Can you hear me?
Good morning,
Yes,
sir.
sir. Yes, good morning.
So, I got the schedule for the MTPs yesterday night. I think they go on till 1 o'clock in the afternoon on Saturday. So, the exam will begin on Saturday uh, at 2:30 p.m. So, I'll send you the schedule, meaning the order in which I um, will conduct the exam. Um, Basically by tomorrow. Okay.
Sure, sir.
Yes,
Thank
So in the last lecture, um, we essentially covered, finished issues concerning power calculations. Uh, uh, you know, we are already done the amount of power draw under one gas condition, and then we discussed the decline in the power draw due to in the presence of gas, uh, and I pointed out that the book provides. This is the book. I think I should give the reference to, so it's easy. Um, right. So here it is, figure 832. So figure 832 of the book essentially provides the decline. So this is 1.0. When there is no gas, this is defined as Fg divided by, um, yes, hence by um, pumping rate. So it would be, I guess, hence by diq. And um, there's a sharp decline beyond a certain point due to the formation of gas cavities. This is due to formation of gas cavities. And basically, the book says that you basically should not operate. So this is the region where you should operate. Otherwise, small changes in the gas composition, in the gas flow rate, will cause massive declines in the power draw, which is not good for the reactor because it causes massive stresses, sudden changes in the impeller speed. And I also told you that there is a formula. It's not quite expressed in this form, so I've not given you the original reference, but it reduces to this form if you work your way through it. And basically, it says that this Pg over P0 comes down as the fifth power of 1 over the fifth power of uh, the gas flow number, and uh, the there's a certain constant which depends on various. Now, this could be used as an analytical formula if you can't find what you want in the data that is provided in the book. Okay, so the next thing we did was power required for a gas, and I mean, I don't know. So this I actually need to take a look at it more carefully. I know that something is wrong with Doran's work, and I think I tried to explain to you. Um, this is the formula in Doran. and I suspect somebody needs to check that this will work if I mean I can see here, I did the integration. Um, if basically what I told you was that the formula given in Doran is this one here, and the formula given in the papers is this one here. And basically, I think that she's assuming incompressible flow, because if the gas, if this, take a look at the derivation, um, this is the work done for expansion of the gas, basically. As the gas moves from the nozzle from which it is coming out all the way to the top, then the work done by the gas, this is coming from the Bernoulli principle, which I can show you in a minute, is essentially dP over rho, and rho, it turns out, is P over RT. So you get the expression on top, RT ln P over PCPI. So this is actually from P0 PI P0. Sorry, that's PI. So this gives you PI over P naught. If this were not, if the pressure didn't change too much across the height of the tank, then the pressure would remain constant. And in that, so rho, in that case, rho would be a constant. And in that case, I suspect this would go through without, I mean, I hope so. I hope that that is the only difference between the two. But I'll check on this once more to make sure that I'm right. I certainly know that this is the correct formula in several papers. And Doran's formula I have not seen in any paper. So uh, my sense is that they are the same, but for the difference that I have just pointed out. But I will check and let you know. So if you do the homework, unless and until I tell you, uh, give more clarity to this, feel free to use Doran's formula. And then we went through the criteria for mixing, and I basically defined the circulation time, and I mentioned that the mixing time is nothing but 5 times the circulation time. And then I also told you how to estimate the mixing time. This thing on top is really experimental method, right? This is like actually doing the experiment with a sensor. And as I told you, it is in your lab, except that instead of this damped periodic function, what you get is an exponential function, which suggests to me that these large circulation patterns are only observed in large reactors, not in the small reactors that we have. And then coming to actually not measurement but estimation of mixing time, I basically told you that this was the formula. When HL is equal to DT and the flow is turbulent, there was a minor error which I have now corrected. I did not put down, these are all formulas taken from the book. So I should again mention where this is in the book. This is this is the formula. This is 822. So this is equation 822. Equation 822 of Doran. Now, and then I told you that this equation provides a reasonably good prediction. And one special case is that when you put in the power, the particular this experiment was done for HL equal to dt. So if you calculate VL and if you put in the right value of P0 for turbulent flow, which is NP prime multiplied by rho n sub I to the cube and di to the power 5, you actually end up with a formula that shows that the mixing time is independent of the Reynolds number, as expected from this figure, which which also I've shown you, but I'll mark it out. And it depends only on the impeller type, because this NP prime varies with the type of impeller, whether it's a Russian impeller, um, whether it's a marine impeller or anchor, what have you. And it is also inversely proportional to the square of di over dt squared. So this is consistent with the picture in the book, which is shown over here. So this is the formula, and if you compare this formula, this is the formula we have derived. Uh, you can see that this formula is more or less consistent. Yeah, it depends only on NP prime. So this formula, if you move Ni to the left hand side, you get Ni times Tm equals 5.4 1 over NP prime to the power 1 over 3. So notice that here in this, we are plotting on the left hand side Ni times Tm, which is the dimensionless mixing time. And that formula shows that the dimensionless mixing time is simply dependent on NP prime and dt over di. So it depends only upon the properties of the impeller. It is completely independent of the Reynolds number. Okay? So, here's a trivial application on now. This is the type of simple application. So let me point out that the examples that are done within the book are invariably trivial. You just they give you something, and within 1 second you can solve it. But the problems at the back are not so simple. So she has not put any challenging solved examples. All the challenging examples are at the back. So I'll give those to you, and maybe you should try them out once the minor ends. This example is basically asking you for estimating the mixing time. A baffled fermenter with tank diameter and liquid height, both equal to 1.2 meters. So you have dt equal to ht equal to 1.2 meters. It is stirred with a 6-blade downward pumping hydrofoil impeller. So this is a relatively, well, she claims somewhere earlier in the book, if you read the chapter, this is a new kind of efficient impeller. The impeller diameter is approximately 0.4 meters, and the stirrer speed is around 100 RPM, 1.5 per second. The viscosity of the medium is 10 to the minus 2, which is, I guess, kind of high. And the density is 1000. Estimate the mixing time. So in this problem, actually, you're given everything that is required to estimate the Reynolds number. This is n sub I. This is um, p sub I cube, and this is rho, and this is mu. So calculate the Reynolds number. Once you know the Reynolds number, you can either go to this equation. Actually, he's using straight away. You can use this graph, because this graph is data for dt equal to hi, and you can find out that the dimensionless mixing time is so much, and therefore np prime. So this is np prime. This is taken from table 8.2, and the rest of it. This is di over dt whole squared, and this is n sub I. So she's using this formula over here, 824, to calculate the mixing time. Now, these are the trivial examples, but I would like to cover is two slightly more subtle issues. Um, one of them actually I ought to have covered earlier, but I think now is a good time to do it. But I'll get to that later on. So the first question I want to address is, I think, an important question, uh, which really gets to the heart of scale up. I mean, I think right in my first lecture, I mentioned that this stuff that we're doing, this is really the heart of engineering. I mean, all the kinetics and all that stuff we did, node model, this model, that model, none of those things change with scale. If you do an experiment in a shake flask, or if you do it in a 10,000 liter reactor, the kinetics will be the same, provided you can maintain the same conditions. And by that I mean that if you go from 1 liter to 10,000 liters, if you can maintain the same dissolved oxygen levels, the same pH, the same concentration of sugar, if all this can be maintained in a 10,000 liter tank, there is no reason why the cells will grow any differently. The fundamental problem, as I pointed out, was that when you go to the 10,000 liter scale, it becomes really hard to maintain the conditions that you got quite easily in the 1 liter reactor. And the reason for that is, in this case, as we will see shortly, it's extremely difficult to get good mixing in a large tank. And the reason for that is that the power that is required to get good mixing is basically so high that there is nothing out there that can give you that kind of power. So here's a quick calculation. Um, Actually, easier to just explain to you what is done in the book. So let me see. Huh. So here is an explanation of. So I'm gonna now. We're getting a little bit closer to the business of scale up. Um, so what she's trying to do now. So this is the she's basically gonna show the main idea that we're getting at in this argument is that the power that is required, and she's doing it for ungassed systems, the power that is required to uh, run the amount of power you must draw to maintain good mixing uh, scales as the volume in the reactor to the power 5 over 3. As you can see, this means basically that if you treat 5 over 3 as approximately equal to 2, then it is going increasing as the square, approximately as the square of the volume, which means if you increase the volume tenfold, your power requirements will increase 100-fold if you want to have good mixing. Well, how does that argument go? Well, we can see now how that argument goes. So, suppose you want to maintain the same mixing time in a small and a large reactor. So I think she uses the notation subscript 1. The subscript 1 is used for the small scale reactor, and the subscript 2 is used for the large scale reactor. And so supposing you want the mixing times in the two to be the same. So this is TM1, which is the mixing time in the small reactor. And on the right hand side, we have TM2, which is the mixing time in the large scale reactor, right? And she's using basically the formula that we have just worked at. This is the formula, this formula. So you can see that TM is essentially uh, inversely proportional to the power per unit volume, right? It's power per unit volume to the power 1.3, but there's an inverse relation. And then it is also inversely proportional to the 1/3 power of the ratio of the impeller to the tank diameter. Okay, so this formula is clear. Now, the thing that you want, this is an important point that we will address once again, is that whenever you do scale up, you maintain what is called geometric similarity. That means that all dimensions, such as impeller diameter, the off bottom clearance, the baffle size, the width, everything scales in the same proportion. So if the diameter goes up, say K fold, the tank diameter goes up K fold, then impeller diameter will also go up K fold. The baffle, this is, so one always does a scale up with geometric similarity. And you might ask why that is the case. Well, so there are actually two things that can change as you scale up: the geometry and the hydrodynamics. And the hydrodynamics itself is so hard that people just try to keep the geometry as similar as possible. Uh, and as you will see that even despite the similarity, one runs into serious problems. So if you maintain geometric similarity, then that means that dt1 over, it means that this term is the same as this term, because you're maintaining the same ratio. dt over di or di over dt is the same in the small and the large tank reactors. So they're both equal to 1. We can ignore this term. Okay? That means that you arrive at equation 826, which basically says that, so the density of the fluid is, of course, the same in small scale and large scale. So this rho 1 and rho 2 also disappear. And you are left with equation 826, which says that dt1 to the power 2 over 3 multiplied by VL1 over P1 to the power 1 over 3 equals dt2 to the power 2 over 3 multiplied by VL2 over P2 to the power 1 over 3. Now, basically, he's going to take the cube of both sides, and when he takes the cube of both sides, she arrives at this formula: P2 equals P1 equals dt2 over d1 squared multiplied by VL2 over VL1. This has simply been, you've just cubed it to get rid of all the fractional powers. So you can see that P2, I mean, if you want to write this, I would write this as P2 over P1 equals dt2 over d1 squared, right, multiplied by VL2 over VL1. Now, keeping in mind that 2 is the subscript for the bigger system, you can see that basically it is going as the square of the diameter and VL2 over VL1 as the linearly with volume. Now, another result following from geometric similarity is that VL2 over VL1 is simply dt2 over dt1 cube if you have geometric similarity, right? And why is that the case? Well, the reason is that every dimension is increasing in the same proportion. It's as simple as that. I mean, the volume we know to be equal to, let's say, pi dt squared over 4 multiplied by ht, right? And let's say this is vi1 and this is okay. So in fact, everything scales as some power of the diameter, simply because, and let's say vi2 equals pi multiplied by dt2 squared divided by 4 multiplied by ht2. Now, because dt2 over dt1 equals ht2 over HT1 equals K, you can easily see just put HT2 equal to K times HT1 and DT2 equal to K times DT1, and you will find out that basically the volume will increase as the cube of, of the size. So essentially this quantity can be written as, you can either write dt2 over dt1 cube, or if you don't like that and if you want to work like her, you can replace dt2 over dt1 squared by v2 over v1 to the power 2 over 3. So you will get this formula if you work with her way, and if you work with my way, you will get P2 equals P1 multiplied by dt2 divided by dt1 to the power 5. Is that part clear? Any questions?
Yes, yes, good.
Anybody? Any questions, anybody? So right there you can see that what is it? So right here you can see that basically your power is going to increase approximately as the second power of the volume. This is quite drastic. So here are some numbers he does. So supposing you scale up the reactor from 1 cubic meter to 1000 cubic to 100 cubic meters. So this is basically from 1000 liters to 100,000 liters. So 100-fold increase in the volume. That means this quantity, uh, here is 100. So that means that the ratio by which you have to increase the power is basically 100 to the power 5 over 3, which she says turns out to be 2000 times. So this number is approximately 2000. It's 100 to the power 5 over 3. Now, in a typical, small scale, so basically this kind of power, 1000 time increase in the power, you can never get. So to give you a rough estimate, I think that in the lab scale, you draw a power of about 1 kilowatt. And if you scale up the process 100-fold, you can pull power up to 150, 200. But such massive power cannot be drawn, so you will never be able to get the same mixing time. Any attempt to get the same mixing time at large scale will fail. So you basically simply give up. You say, okay, man, I'll make a compromise. I can't apply that kind of power. So this is the reason why, you see, new problems are encountered when you scale up that have absolutely nothing to do with um, the biology or the kinetics. This is purely a matter of your inability to transfer uh, something like heat, mass, or in this case, momentum at a large scale. Just not working out. And once you have poor mixing, then your productivity goes down because there are pockets where the liquid is not moving. It's dead space. Cells are suspended there, not receiving the nutrients, not receiving the oxygen. And so these cells are basically producing nothing. This is the reason why you see lower productivities on the large scale. And so that is why when you apply for money from for example, DBT for entrepreneurship, um, they will not give you the final tranche of money unless and until you can show the operation, as they put it, at the large scale. Um, Showing it in the lab, they'll give you like one batch of money, but they will give you another bunch of money only to do what they call pilot testing, which is like at 1,000 liter scale. and then industry will not look at it unless and until you have done this what they call pilot testing, which is somewhere between lab scale and industry scale. Okay, so if that part is clear, I also want to address one more important point, which is also quite relevant, and that is uh, this business of the retrofitting, and this actually turns out that this is an interesting. So retrofitting, the word is typically used to describe going back and making changes to a pre-existing system. Um, so somebody from this department told me that actually he was heavily involved in um, this kind of stuff back in the 80s. And the reason is that the antibiotic industry in India was set up with, I guess, Russian collaboration. The company was called Hindustan Antibiotics. I think they had one plant in Haridwar and one plant in Pimpri, someplace in Maharashtra. And antibiotics were made indigenously. But by the 80s, they discovered that these plants were highly inefficient, that they were drawing too much power. So, and so, by the way, production of penicillin is like the marks the birth of biochemical engineering. This is the first biological process to be scaled up. And his job was to really change the impeller. And he basically bought Japanese impellers, I guess from Hitachi or somebody or Mitsubishi, to make them more efficient. And what we're looking at is a classic example of retrofitting. What is the principle underlying retrofitting? So if you think you have an inefficient setup right now, how will you go about changing it? So in this regard, the first point to be made is that there are certain things that ought to be preserved even though you are going through the retrofitting process. And what are those things? Well, you know, the impeller is actually preceded, as I've already shown to you. The setup is actually, um, uh, maybe I should just show the picture. Um, so, uh, this, here is that paper. This measurement of uh, power required. Actually, I'm not able to find. Um, uh, Here it is. Well, I think it'll have to pass. Maybe I'll just draw a picture. So, um, this, thing I've already shown. Um, if this is your reactor and this is your impeller, then over here you have what is called a drive with bearings on it. And this is, of course, connected to a motor. Um, so your motor turns, transfers the power, and in between there might even be a gearbox. Um, so from the motor, the power is transmitted via a gearbox or a belt drive to basically transmitted to the drive, and the drive then has bearings on it, transmits the power to the this is the impeller shaft, the shaft, and these are of course the impellers. Now, if you want to do a retrofitting, you want to do the retrofitting in such a way that basically the rest of the stuff doesn't have to be changed. So you don't want to change the shaft, the motor, the gearbox, or the drive, right? It would be crazy to redo the whole thing. And so, one criterion, one way to make sure that you don't have to change these things is first of all, just make sure. So one, make sure make sure power does not change. Because if the power draw changes significantly when you change the impeller, you'll have to change the motor and so on and so forth. What you really want is that the power that you're drawing is used more effectively, right? So that it delivers, you get much more for the power that you're drawing. Um, and the second is, well, you also have to make sure that the impeller speed, um, actually, impeller speed, um, actually, sorry, not impeller speed, but torque does not change. So the torque that is being, that is that the impeller is suffering while it is trying to turn the liquid. This also must not change because if the torque increases drastically, for example, it might just break. You want the torque and the power to remain unchanged during your retrofitting. This is sort of the rule of thumb you use when you go ahead. So ultimately, what you want to do is now the main point here is that actually it turns out that just as work is equal to force times linear velocity in a mechanical system that is moving linearly, it is also equal to in a rotational system like this, work is equal to torque times angular velocity. Uh, this you must have studied in for JE. Now you can see that basically, sorry, I shouldn't say work, I should say power. So in a mechanical system that is moving linearly, the power equals force multiplied by linear velocity. We in fact use this, right? We used P0 divided by VI when we did the scaling. And similarly, in a rotating system, power equals torque multiplied by angular velocity. Now, if you stipulate that the power cannot change and the torque cannot change, that means this cannot change and this cannot change, then obviously that means that the angular velocity cannot change. So essentially, it means that your impeller speed n sub I, which is in revolutions per minute or revolutions per second, right? It's not going to change during the retrofitting. Now, the next thing so now we can simply go back to the argument. So here is the argument, right? Let me simply read it out to you. So I'm reading from over here. An important requirement for retrofitting is that neither the drive nor the drive assembly be modified. You don't want the rest of the stuff to be changed. This is because the expense associated with replacing the shaft, seals, bearings, gearbox, and possibly the motor itself adds considerably to the overall cost. Therefore, ideally, retrofitting is carried out so that the power draw and the torque in the new stirrer system are the same as for the old system. So, this is a key point here. Now, the next statement basically says that if you keep the power and the torque the same, then basically the impeller speed has to be the same. So, she's using the same equation. You go back to equation 8.5, you will see it's exactly the equation that I've given to you, that the power is proportional to the torque multiplied by the angular speed. So from equation 8.5, maintaining the same power and torque implies that the operating stirrer speed N sub I will also be the same for the old system and the new system. Now, coming back to so here is an equation that is saying, okay, if these new and the old impellers consume the same power, right, then this condition has to hold. NP prime, this is all assuming turbulent regime. NP prime times on the left hand side is the new system, and on the right hand side is the power requirement of the old system, right? Now, whether it's the old system or the new system, the density is the same, so rho cancels out. And as I just mentioned to you, if not only power but also the torque has to be the same, then that means the impeller speed of the new and the old one is also the same. So this also disappears. So all you are left with is this. You are left with this relationship di to the power, the, the impeller diameter of the new one to the power 5 is equal to this, which means di new has to be equal to this is the ultimate formula you get. Now, NP prime for these newer impellers that are coming up in the market is higher than I guess have a lower NP prime. So basically, it often turns out that because this ratio is basically uh, greater than 1. The old ones have a much higher NP prime than, like the Rushton impeller, than the new ones. So it turns out that actually you end up getting larger impellers, even though you're operating under the same conditions. And these larger impellers have much better properties. They do a better job of mixing the gas. They also do a better job of uh, pushing the liquid around. So, you're operating at the same power, right, as you were in the past, but this power is being used much more efficiently if you follow the retrofitting design principles here. So here are two uh, immediate applications of this stuff that we have covered. How do you retrofit? How do you go to a place that is running inefficiently and modify the system to make it more efficient? And the second thing that we saw was that the real reason why things fail at the large scale is that the ability to transfer stuff at the large scale becomes really hard. So I gave you two simple examples in heat transfer and mass transfer by using purely geometrical arguments. That the heat generation increases with volume, the heat dissipation changes with surface area. Therefore, you will have problems on the large scale unless and until you start introducing cooling coils or something like that into the bulk of the medium. Um, uh, Similar things happen in oxygen transfer. If oxygen is being transferred not by bubbling air through the system, but if you transfer it only through the surface, you have major problems when you scale up because oxygen transfer is taking across the surface, but it's being consumed in the bulk of the volume. So as you increase the scale, due to the decline in the surface to volume ratio, the transfer of oxygen into the system doesn't increase as fast as the rate at which it is being consumed. So I will now sort of get to the last point, which is um, basically expanding on what I have already mentioned. So we've already seen that mixing, if you try to preserve mixing times from the small scale to the large scale, you're doomed. The power requirements are too heavy. So you might say, okay, man, then what should I preserve? And what I want to show you is that no matter what you preserve, there are other things that you can preserve. You will run into some problems. So scale up then becomes a kind of an art. You have to decide what do you want to scale up so that everything else will suffer. But the art is to minimize the suffering that is caused in the other metrics. So if this part is clear, I'm going to move ahead and finish off this chapter. Um, so any questions on what has been covered?
No, sir, it's been pretty clear.
So the last topic that I'm covering is actually not from uh, not from Doran, but from Schuler. Um,
So
so the
just
last,
one question here.
uh-huh.
So why did we take the value of NP prime for oldest to new as greater than 1?
Because that's actually what it's all about. New impellers are being designed. They have so the Rushton impeller has among the highest NP prime. These are experimentally measured, right? So if you take a look at the, actually wait a second, let me. These are given. Um, so I mean, this topic I have not covered. Um, so here's an example, right? So this table 8.2. Right. Okay. Now you can take a look here. This is the this is almost all impellers are old impellers are Rushton impellers. The NP prime is 5.9. The next generation of impellers, uh, the Rushton turbine, the impellers are completely vertical. You know, the next generation was pitched blade, downward pumping, and you can see that it has an NP prime of 1.8. And even the newer version, these are the ones at least she's talking about. These are what are called curved blades. So I'll just show you the pictures in a minute. Either curved blade or hydrofoil lightning. So these are, so if you can think of this, the Rushton turbine is from the 50s and 60s. The pitched blade turbine is the next generation. And when she wrote this book, which I guess is sometime in the 2000s, um, it's the curved blade and the hydrofoil lightning that was that have become the market leaders. And you can clearly see the decline in the NP prime. And what is NP prime? It is basically this part. This is NP prime. And why is it becoming lower? Well, I guess, you know, so basically, uh, in this case, you can say that the power draw is essentially the scaling, the proportionality factor NP prime is going down because these impellers are doing, I guess, a much better job of using the power that they are getting to agitate the liquid, better momentum transfer. Um, so here are the pictures uh, as you go from generation to generation. So I'll just start from. I think I've shown these pictures, but I might as well. I'm hoping that in the labs we will have an opportunity to show these things. Um, so here is the Rushton turbine, right? Just notice that this thing is sitting perpendicular to the disk. So this is the disk, and these are the things that are pushing the liquid. They stand orthogonal to the disk. So it's just literally as the movement is it's just pushing. Uh, it's like pushing a wall basically. And in the next round, the next generation, they started marketing these pitched blades. So this is the picture I've shown this to you. This is the 6 blade. This is the Rushton impeller on the left side. And on the right side is the pitched blade turbine, in which all they did was to just pitch them at an angle. That's the next generation with an NP prime of I think 1.5 or something. And then the third generation is the one shown over here. Um, right here. So this is the curved blade. You can see that instead of pitching it, you have literally curved it, and it's like a curved thing that is carrying the water with it. So this is the third generation curved blade. This is one thing that they say is great, and the next one is this lightning hydrofoil impeller. The picture is, I mean, if I blow it up, it seems to me like a minor modification of the pitch blade, but this also has a very low NP prime. I mean, I should point out that because the theory of turbulence is not developed, most of this work is empirical. But obviously, it has huge financial repercussions since if what Villadsen is saying is correct, 70% of the problems are related to mixing, then, um, as empirical as this work is, it seems to lie at the heart of most of the problems. I guess shouldn't be surprising. If you don't understand something, it's not surprising that it will be at the heart of the problems you encounter. So, does that answer your question?
Yes, sir, it does.
Okay, so the last topic is this is taken from Schuler, and the purpose of the last topic. So we have already seen that um, uh, preserving mixing time over scale up is, uh, in a sense, practically impossible. So what I want to show next we show that it is impossible to preserve it is which will not be surprising at all. It is impossible to preserve everything in scale up. And the reason is really pretty much the same. I mean, everything scales in a different way. So if you try to preserve one thing, the next thing will suffer. That's sort of the basic idea I want to sort of get through. This discussion is taken from section 10.2.4 of the book by Kargi and Schuler. And here's the basic idea. So so remember that I mean, when we talked about the heat transfer and the mass transfer, we basically said that we run into problems because the surface area and the volume scale in different ways. One goes as a square, the other goes as a cube, and heat generation goes as the cube of the diameter. The heat dissipation goes as the square of the diameter. So you run into problems in the large scale. So actually, it turns out that everything scales in a different way. So here is a table, not just these parameters, but others too. Like so, let's put a table here. So here is the parameter, and we have many of them that we can consider. Like we can consider mixing time. We can consider the impeller speed. We can consider the impeller Reynolds number. And another important parameter which we have already seen is, for example, the power per unit volume, right? And actually we know their importance as well. So the mixing time, this is actually, it determines mixing. This V sub I, I've not covered this section. I skipped it because it will be covered in mammalian cells where it's important. The impeller speed is important for determining how much shear is experienced by the cells. And this is a particularly important problem in mammalian cells. In microbial cells, they can tolerate very, very high degrees of shear. But in mammalian cells, if you expose them to any shear, they just tear apart. So the type of reactor that I have shown is rarely used in mammalian cell cultures. I mean, there actually many of the reactors actually have no impellers at all. They either work on bubbles, simply bubbles dispersed like an aquarium through the reactor, and even those cannot be sent at a high rate because the cells often attach to the bubbles. They surround, they lie at the bubble water interface, and when the bubbles come out, the cells just tear apart. And another way is to simply provide oxygen from the head space, that is to say, above uh, the air liquid interface. You just pass oxygen through it and hope for the best. It's basically like a shake flask. That's it. But in microbial reactors, this is not a problem. And then, of course.
So, but I had a question.
Uh-huh.
So, why are mammalian cells even cultured at such a large scale? Like, what use do they have, like, industrially?
Oh gosh, I mean, all virtually the entire therapeutics industry, all these companies like Amgen, Genentech, and actually, by biotherapeutics, I mean the entire industry. For example, is insulin, right? I mean, it's a it's a human protein that is now made. Uh, Earlier in the good old days, it was made by going to the slaughterhouse and you know scavenging the pancreas of pigs. But I mean, that simply is not enough to sustain. So the huge industry has developed to make recombinant proteins, primarily therapeutic proteins. Now these therapeutic proteins, um, actually, because of the, and this molecular biology, right? I mean, eukaryotic cells um, do post-translational processing, whereas bacterial cells don't. So initially, they tried to make them in bacterial proteins, and the proteins were not quite good. They were not because the bacterial cells just don't do the post-translational processing, and so the proteins end up being not quite like the ones we see in humans. Well, then they tried these yeasts, which are also eukaryotic cells, and tried to make the proteins in yeast. And they do some post-translational processing, but it was found that they don't give you exactly the same proteins that you have in humans because the post-translational processing is different. Basically adding certain sugar groups to decorate the cells decorate the proteins with certain carbohydrates, and because these are slightly different, it can lead to immunogenic reactions. So in the West, in the US, in Canada, and West Europe, they use only mammalian cells. So they use these. The most common ones are called Chinese hamster ovary. Uh, they're extremely expensive, but because they have money, they give priority to safety over money. But in India, all these proteins are being made by using yeast, and I mean, we're supplying literally to the entire third world. I mean, Africa, all of the Far East, um, South America, they're all being supplied by the Indians. I mean, all these proteins. So, but the largest, I mean, we're supplying to the poor people. I mean, the biggest manufacturing is done using mammalian cells. It's just that that's not a big deal in India because it costs almost 5 to 10 times the cost of making the same protein in yeast. And if in India they find that it kind of does no harm, they just move ahead. So that's the reason. Is that clear?
Yes, sir. Thank you.
Um. So, so I think that there is a course that this Madhuresh Sumit, he was in the business of making mammalian proteins in Pfizer. Uh, he's expected to sort of, I think he's already teaching that course this semester as an elective. Okay,
Yeah,
so the Reynolds number
I guess
decides.
animal cell technology.
Yeah, that's mammalian cells, right?
Yes, sir.
Uh-huh. And this P0 over VL is important not only in mixing, it's extremely important, as we will see later on, for determining the mass transfer coefficient. So these are 4 different parameters. Now, the scaling, which is to say their dependence on the impeller speed and the diameter, is quite different. I mean, we've seen that um, um, this goes as 1 over n sub I over scale. This is equation, I guess it was equation 822. I can't remember now. But this is all over the place. Right. So here it is. This formula here. It shows that since dt over di is constant due to geometric similarity, it is scaling as 1 over n sub I. Okay. And vi is essentially nothing but n sub I d sub I. This scales as, if you go back and take a look at the formula, n sub I d sub I squared, because it's actually rho times vi times di over mu, and since this is n sub I d sub I, it scales as n sub I d sub I squared. So notice that whenever I say scales as, I'm assuming here that when you go from the small scale to the large scale, rho and mu are unchanged. So the only thing that matters is the product, n sub I d sub I squared. And this scales as uh, n sub I d sub I, this is n sub I cube d sub I squared. And why is that? Well, we have already seen that P0 scales as n sub I cube di to the power 5. That we've already seen. And the volume, of course, will be proportional to di cube. As I told you, in scaling, if you maintain geometric similarity, then everything changes with only one dimension, right? Because all other dimensions are proportional to this dimension. So VL is proportional to the tank diameter, is proportional to the cube of the tank diameter, because the height of the tank is proportional to the tank diameter. But the impeller diameter is proportional to the tank diameter. So therefore, if VL is proportional to dt cube, then VL is proportional to di cube. Maybe I'll just put this down. It's easy to see that VL goes as dt squared multiplied by ht. But we always have ht as proportional to di, right? ht is always proportional to dt. Whenever you do scaling, the proportions don't change. So we can say that VL must therefore be proportional to dt cube. But that means that VL is also proportional to di cube, because di is always, it is in fact proportional to whatever dimension you choose. So if that part is clear, this comes out of geometric scaling, then it should be clear to you that we can write over here that VL is proportional to di cube. But that means that P0 over VL is proportional to n sub I cube d sub I squared. That's the result we have over here. So I think that you should now be able to see where these are coming from. And given that fact, now let's start the argument, right? So I'll show it essentially by saying, um, so suppose you decide, so what I'm trying to show is that if you try to preserve the mixing time from the small scale to the large scale, right? So if you make sure that mixing time at the small scale is the same as the mixing time at the large scale, you will find that all the other parameters will not be the same, simply because they scale in a different way. So here's an example. Suppose you decide to preserve mixing time PM over scale up. So you say that I am going to keep TM1. So I'm going to keep TM1. Once again, 1 is for small and 2 is for large. Supposing I want to keep the two mixing times the same. Correct? And let me also define over scale up. By a factor di2 over di1 equal to 5. So I'm saying that I have, let's say, increased my diameter by a factor of 5. And over that 5-fold increase in the diameter, I insist that I want to keep the mixing time the same. Correct? Okay. Now, actually, let's not do mixing time. Let's do, let's say, V1 equals V2. Okay. Now that means that I must have Ni1 Di1 equal to Ni2 Di2, because Vi is nothing but N sub I D sub I, then this relationship has to hold. But that means that I must then make sure that Ni2 divided by Ni1 is equal to essentially 1 divided by Di2 divided by Di1. So if I, which is basically nothing but 1 over 5, I mean, that's obvious, right? If Ni Di is to be held constant, then that means if I increase Di 5-fold, then I must decrease the impeller speed 5-fold. So if I want to keep the same impeller speed during scale up, I better decrease uh, the impeller speed by a factor of 5 during scale up. But if I do this, then all the other things will not be preserved. But then none of the other parameters are preserved. So for example, if you take a look at Tm2 by Tm1, now we know from the scaling that Tm scales as 1 over N sub I. So that means this is 1 divided by Ni2 divided by Ni1. But since we chose Ni2 over Ni1 to be 1 over 5 to preserve the impeller tip velocity, it turns out that our mixing time will have to be, this will be 1 divided by Ni2. This is 1 over 5, so that's 5. So your mixing time has gone up by a factor of 5. And if you take a look at the Reynolds number, so this is REI 2 divided by REI 1. This is going to be now NI2, right? And this is DI2 squared. And this is Ni1, and this is Di1 squared. So you can see that basically this is Ni2 over Ni1 multiplied by Di2 divided by Di1 squared. Well, Di2 over Di1, we have a system in which this ratio is basically 5. It's not, my pen is not responding. Can you hear me?
Yes,
Yes.
Yes, sir.
I mean, I don't know. My pen is not completely idiotic. It stopped. I think my system has, I guess, just frozen. Well, so this is 5. This is 5. And we found Ni2 over, this is 1 over 5. And this is 5 squared. So you basically find that your Reynolds number has gone up by a factor of 5. So, this argument can be made even for the the last one is, I think, the P0 divided by VL, which scales as Ni cubed di squared. So, repeat the same argument. This is Ni2, Ni1 cubed, di1 squared. And you can see that this will also give you some other number. It turns out that this decreases fivefold. This, it turns out, will decrease fivefold if you go through this argument. So you can see that when you try to now, so you tried to keep the mixing time the same and the Reynolds number, sorry, you tried to keep the impeller speed the same in your mixing time, Reynolds number, power per unit volume, they changed. You try something else and the other three will not be preserved. So the art of scale up is basically to pick that one that causes the least damage. Everything is going to change, but you look for least damage. The most common, this is like a, if you go to the industry, the most common one invariably used for scale up is this one. They try to preserve the power per unit volume. And the reason for that is that this is intimately connected to the mass transfer coefficient called KLA. And the sort of widely accepted belief is that it is the inability to transfer oxygen that is screwing people over in the large scale. And this parameter is most important for preserving oxygen. But there's an interesting paper, maybe I will put it on, written by sort of the leading guy in this area, the guy who developed the penicillin technology. I'll put it up on the thing where he says, and it's an interesting paper because it also talks about the history of biochemical engineering. It is actually based on this work, this kind of work, not the poo-pah recombinant protein and this and that is going on. That is not where the engineers contributed. The origins are in this kind of work. Basically, they found that in penicillin production, they were unable to make a lot of penicillin simply because when you scaled up the process, not enough oxygen was being delivered. And then these chemical engineers came and told them just how to do that. And that's when production went up and it became a valuable compound. Until then, they were not even making enough to make 5 people survive. I mean, they would just make enough in their dinky little shake flasks. And, it would all be over and the guy would die. So, as dull as the stuff is, it is lies at the heart. So, you can read that paper and he talks about something we have not done yet. So, essentially, I think he says that at the 5,000 liter scale, it is oxygen that is typically the limiting thing. At the 50,000 liter scale, it is heat transfer that becomes the real problem. You have to find good ways of cooling. And then he mentions also a few other things that often happen. This is just for those who are interested in seeing what is going on in the industry, or for those who want to, get into the entrepreneurial business and actually make something in the real world as opposed to shuffle spreadsheets around in a bank. Okay, so if that covers, I think we're past time. If there are no further questions, we will end this and meet at 5 p.m. For the session. Is that part clear? Any questions?
Yes, sir.
Yes, sir. Thank you, sir.
Yes.
Okay.
Thank you,
All
sir.
right.
Good afternoon, sir.